Dude, AMCR, research changes lives.
Negative
That's
words.
plus or minus. Some New York City.
It's a like nerd.
That is so pretty.
Like maybe like maybe amongst like research.
Yeah, like let's say you're going to like international conference. That'd be up there.
These international kids like they're great. Seem really
They won't be tired after huge physicists.
Putting together a one-time
who's invested in
Word? We actually found a good people for that.
really?
Is there any Houston students here?
No.
I don't think so.
Oh, it's just like
We found shuttle
I mean, yeah, because they look like one point, it's 30, 20 or 30, right? It's just going to be good stuff. Freezing through
Only super flag, only model watch,
Kill Cooper flag. You shoot Cooper flag.
Constantinople will take this place. We got 2 more to take this place.
I mean, I can never be done. And we had the number 2 and 3. He's been in the conference.
Wait, are they still signing here?
What do you go to? Harper just declared for the and he's been like, there's no reason to stay.
Yeah.
And, you know, with them goes his future.
Did you guys have to on stage or you got the Blizzard twins?
I mean, yeah, the program, Duke's program, I don't know,
I think we already have like 4 to 6 people on Google.
Problem is nobody stays. Everybody just uses because I made a requirement that you complete right here. On each day.
Can't believe you're the one.
No, he's gonna come back.
You're
No, he's gonna move back up to
Yeah. Dude, after his heart attack, he could take his life.
he doesn't really like in the G League he's
No Zoom meetings.
I think he's trying to take it light because of that.
he'll be back though. It has to be after the primary. In 2050.
I don't think he'll be there after.
I know Roddy gonna retire his sometimes they're
Have you
Literally,
We started 12 years ago.
and then a brief
Oh yeah.
everybody was doing that. Yeah, I know.
Yeah. Yeah.
They had me thinking that you could do it.
Come on, Jack, I'm over there.
Dude, Dragon Ball could have perfect.
He exposed himself.
Too good. They were like minus 98%, $5. Who's not taking the 98% deal? They lied to you. No dragons was
Bro, it's like where they change the price from like $30 to $35 and they said
change the price from $30 to $35 and then the sale brings it down to $33.
Yep.
Greatest deal of all time.
He did it just for you.
Oh my god, the deal is exclusive.
Oh yeah. Oh, you sure? This deal was exclusive. What's it? It's never been
Your
exclusive.
deal. This is your deal.
Make you feel special.
I remember going on YouTube just to see like what songs people could make in lessons.
Oh yeah, I looked at like the top 10 most singing
Yo, how to pseudo jailbreak your phone to get free Dragon Ball Z. Just on the phone or
Wait, I had Aries. I had this semester.
Nobody knew what
I had Aries. Metal person. I had a metal one. I was balling out. Didn't even take the steam too. I was proud of it. Yeah, I didn't do anything.
Hello? Hello? Yeah, please.
All right, everybody. Thanks for attending the Innovation Expo right before this, and coming to this talk as well. So I just want to welcome everybody back. We're going to have a few people coming in, but we're just going to start for now. First, I want to welcome Dr. Douglas Stone to give his talk on conceptual thinking in physical sciences. Dr. Douglas Stone is a Carl A. Morse Professor of Applied Physics and a Professor of Physics at Yale University and the Deputy Director of the Yale Quantum Institute. He's a theoretical physicist known for groundbreaking contributions in optical physics and quantum photonics. Also, his acclaimed book, Einstein and the Quantum, The Quest of Valiant Swabian, won the Phi Beta Kappa Science Book Award. Dr. Stone is a Rhodes Scholar with degrees from Harvard, Oxford, and MIT, and has earned honors including the Willis Medal and the Optica's prestigious Max Born Award. And I can go on about his accolades, but I know him personally. Last semester, or maybe last year, when I took his Einstein and the Birth of Modern Physics, and I was able to know him academically and personally. I think he has this fantastic way of thinking about science, and I'm excited for him to share with you today. Take it away.
Thank you, Ian. That's such a nice introduction. I really appreciate it, and appreciated your hard work in the class too. Okay, so this is a special special customized talk that I've never given before because Xeon said I should kind of do some personal stuff and some science stuff and mix them in. It's going to be mostly science, but a little personal. And because of that, I'm going to talk about Einstein, who's pretty well known, and me. So that's why I have Einstein as mere mortals. I'm very aware of the fact that anything that would seem like I'm comparing myself to him, even though my first initial is A, which is Ein in German, and Stone is Stein in German. But other than that, I'm not comparing him to me. But I am going to tell you some stories, and there's a little bit of commonality. Okay, so this is Einstein in 1912 when he was about 32. If you don't recognize him, that's the same guy. Okay, and then this is the mere mortal when he was 32. Okay, mere mortal. Well, I was very interested in math and science fiction growing up, and I certainly thought I might be interested in physics and so on. So here's some kind of thing I was reading, Isaac Asimov Foundation series and things like that. And then I was also very interested in history and philosophy and even language. So I kind of didn't know what I wanted to do, and I'm old enough that we were in a big Cold War with Soviet Union, and Vietnam was going on. I didn't have to go, but it was close. And science was not so popular then as part of the military-industrial complex. So I just, when I got to college, which was Harvard, I decided, well, I'm interested in lots of stuff. So there was this weird major, I don't know if any of you have ever heard of it, called social studies, which is so embarrassing because it sounds like middle school, but it's actually an elite major at Harvard. And you learn about famous social thinkers, Marx, Weber, Freud. I'm sure they're going to be put in receivership soon by the Trump administration. But anyway, so in my junior year, I took this physics for non-science majors course called Space-Time in Motion. The professor's name was David Laser. I kid you not. And it was great. And they had us study Einstein in a fairly serious way, like actually solve little problems. So that was very much of a kind of reawakening of, wow, I really enjoy this. I'm so curious about it. This is really what I want to do. So I switched my emphasis to physics as a junior and started taking those classes. It was too late to actually get a physics degree at that point, but then I was lucky enough to get this scholarship to Oxford, so then I was still kind of in between worlds, so I did physics and philosophy at Oxford, but pretty much decided I would go on in physics if I could. And so I ended up getting a PhD in condensed matter physics at MIT, and I kind of forgot about Einstein because if you're doing physics of matter on Earth, there's not as much relativity as there is if you're doing high energy physics or astrophysics and so on. Einstein is not a ubiquitous presence, and I just got to work, tried to get a job. Oh, this is me in graduate school on the MIT physics department soccer, and the guy with a lot of hair in the middle. I remember making the transition from an insider to an outsider in physics, or from an outsider to an insider, actually, in the sense that, there's a certain mystique about doing physics, particularly theoretical physics, which is what I ended up doing. And so could you even do it? And you need to kind of, it's tough on your nerves because you have to learn so much before you can try to be creative. You really can't just say, well, and some people try, but basically you need to build a big foundation before you can try to be creative. So what if you have no ideas? That's always in the back of your mind. Anyway, it worked out. But I remember, people thinking there was something sort of mystical about physics reasoning, very mathematical and different from the kinds of logical arguments you might make in other fields, which I still had a good memory of being in those other fields or learning about those fields. And so my incredibly insightful answer to that is no, and a little bit yes. So no, it's not that different, and I'm going to show you examples of logical thinking and just clear conceptual thinking. They're not highly mathematical, that were incredibly important in this talk. But yes, there are people who are brilliant mathematicians, and I can't really imagine doing some of the things they do. So, you know, there's some of both. But I would say that Einstein, the most famous and certainly one of the greatest 2 or 3 physicists in history, scientists in history, he was very much on the conceptual side, and we'll learn a little bit about that. Okay, so what about Einstein? Well, I was reacquainted with Einstein because I was working in a field called quantum chaos, which I'm not going to try to explain, but I wrote this paper about it for the Physics Today, not a technical, semi-technical paper, and it came out in the year 2005, which was called the something year of physics, something like that. I don't know. So, anniversary year. What was the anniversary of? Anybody know? What would 2005 be the anniversary of in physics? Oh, this is so disappointing. Sian, you can't answer. Okay, you can answer if you really need to. Okay, what was the?
Is it the photoelectric effect?
Kinda, close enough. Yes, photoelectric effect was part of it. Yes, that's right. So there's something called the miracle year, which I teach about in my class. Between March and September of that year, Einstein produced about 5 papers, and they changed physics. Not just, they weren't all the same thing either. So that's why it's called the miracle year, and many people say there's only been a few events like this in the history of ideas. So we were celebrating that. So this paper had something to do with Einstein, and there's this incredibly cool cover image, which if that intrigues you, I can explain afterwards, but I will not explain now. Okay, so World Year of Physics. I wanted to communicate the excitement and creativity of physics to general audiences, having come from other fields and being interested in writing, not just in scientific papers. I wanted to do that, but I obviously couldn't talk about this very technical thing that I had learned about there, but it sort of inspired me. Why not just try to write something about quantum itself? Okay, so 8 years later, took 8 years, but I did actually produce a book called Einstein and the Quantum, The Quest of the Valiant Swabian. Again, I don't have time, but the subtitle, Quest of the Valiant Swabian, is fun. I'll explain it if you're interested offline. But anyway, the point of this is that Einstein, of course, is famous for relativity theory, right? And not so famous for quantum, but if you know anything about quantum, you know that Einstein said, God does not play dice. He didn't like quantum mechanics. That's a famous quote. So many people don't realize that he was like maybe responsible for most of it, or a lot of it. And that's what this book's about. And it has only 3 or 4 equations, and they're like very simple equations. So it's really for general audiences. Okay. So I wrote this popular science book, which, etc., and I created an undergraduate course. Okay, here it is, the one that Sian took, a little bit of the, blah, 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 you should take this course. The question was, did Albert like this idea that I had? And so I asked him, and he said, the essential in the being of a man of my type lies precisely in what he thinks and how he thinks, and not in what he does or suffers. Okay, it's a little cryptic, so I said, what do you mean? And he said, you will need to have some real math and physics in this course. So the course is not like my book. The book's fun, they get to read it, but they also have to learn a little bit of math and physics. But you don't have to take the course. Blame it on Albert, but not today. You get Einstein, the light version, so there'll be a little bit, but not much. I mean, it's all going to be mainly pictures. Okay. However, this one slide has an equation on it. Okay. So we have to start talking about waves. What are waves in physics? Well, waves are, or were, disturbances in a medium. And they were first described in 1746 for waves on a string, and this guy, Jean d'Alembert, did it. And calculus had been invented about 50-ish, 40 years ago, something like that. And he found the famous wave equation. So the wave equation describes the sideways motion of the string, where it is in the x direction, in the vertical direction at time t, and it's a partial differential equation connecting space to time, and this v squared in the equation is the velocity of the wave as it moves along the string. Okay, so the thing to understand is that a wave is a disturbance in a medium, right? And it's the disturbance that moves, not the string. The string, the piece of the string, if I colored a piece of this string, it would just be going up and down or be staying there. It wouldn't be moving. It doesn't move, right? It's the disturbance that moves, but the medium doesn't. Okay, and sound waves and water waves and other waves are like this. Well, in 1865, this bearded guy, James Clerk Maxwell, figured out that electromagnetic waves obey the same equation. Okay, so light is an electromagnetic wave, kind of gets represented often like this in freshman physics textbooks. The wave is going in the forward direction, and there's an electric field in one direction, and perpendicular to it there's a magnetic field, and it oscillates in space and time and moves at the speed of light, which is 300,000 kilometers per second. I learned today that this was really figured out in about 1670, amazingly, and people believe that the speed of light might be infinite, but by looking at the eclipses of the moons of Jupiter, a guy named Romer figured out that the speed was 230,000 kilometers per second. I said 300,000 kilometers per second, so how do we square those? Well, he was off. It's the first guess. That's how he squared it. But he was close. He was like 75% correct. Okay. So he amazingly was able to figure that out from astronomy and so on. Now, the thing about waves is they interfere. So if you look at this picture here, you see there's some flat regions. There's some kind of piston here oscillating, creating these waves. But where they interfere, there's not much of a disturbance, and that's called destructive interference. Okay? Most of you aren't physics people, right? I mean, it's a variety of people and not, right? Correct? Okay, so I'm not assuming you know too much about this. Okay, so you can cancel out the disturbance, but the medium is still there. And the question is then, well, if light is a wave, what is the medium that supports it? Because we can't really see anything. When light comes to us, we don't see anything because we can't see it with sound either, but we can measure it. Okay, with light, we can't really measure this medium. Okay, so everybody agreed there had to be a medium. So they gave it a name. You couldn't see it. It didn't weigh anything. Couldn't measure it, but they called it the ether, the luminiferous ether. Okay, and of course, you didn't learn about that because we don't believe in that anymore. Okay, but in 1909, after Einstein, but before everybody accepted what he had done, this incredibly famous, most famous living British physicist, J.J. Thomson, said, the ether is not a fantastic creation of a speculative philosopher. It's as essential to us as the air we breathe. So for 60 years, 50 years from Maxwell on, even before Maxwell, there was a belief of this invisible thing that carried electromagnetic waves and light. Okay? Now the problem was with the waves that are in a medium that we knew about, if you are moving in the medium, so if I was on a boat moving forward, these waves would be moving slower. Can you visualize that, right? If I was moving forward or just surfing, right? The waves, you're on the wave and you're going with it. You're stationary with respect to the wave. And so if there was this ether, there should be times when the Earth is going in one direction compared to the ether, because we're going around in a circle. It was hard to believe that the ether was tracking us. At least it would track the sun or something. Anyway, they didn't know, but they tried to detect our motion through the ether and see that the speed of light was not always the same in vacuum. And when we say in vacuum, air is thin enough that it counts as vacuum. Okay, there's not much in air compared to slow down light. Okay, so what was the explanation for this? Okay, it was a puzzle. And with sound and everything, it did slow down or speed up when you moved. Okay, so the idea was that relativity theory will solve this. So Einstein comes to the rescue. Oh, who's this? Oh, there's this guy named Henri Poincaré. Oh, so he said in 1904 that entirely new mechanics results characterized by the fact that no velocity can exceed the velocity of light. He says no observer can really tell if they're in relative motion as long as you're not accelerating two observers in relative motion. You can't say which one is moving and which one is stationary. That's what Poincaré said before Einstein. Okay. Well, there's another guy too. This guy, he actually derived almost all the equations of relativity theory a year before Einstein. And he found many of the same effects as Einstein. Has anybody heard about Lorentz contraction? Anybody? Zihan has. Yeah. So if you're moving, if you try to measure the length of a rod that's moving fast or at near the speed of light, you will find that it's much shorter than when you stop it and measure it. And that's called Lorentz contraction, because it's named after Lorentz, not Einstein, not called Einstein contraction. So what did Einstein really do? He really did discover relativity, but what did he do differently than these very famous, already well-established guys? Okay, so we're going to hear about that. So first, let me tell you a little bit about Einstein's biography. Okay, so before 1905, the miracle year. Okay, so he was born in 1879 in Ulm, Germany, moved to Munich, which is, this is Bavaria and Swabia. Swabian comes into my title. His parents, Hermann and Pauline, and his father and uncle were electrical engineers, so he had a little exposure to engineering and electricity young. They were not religious, they were Jewish, but they were not religious. He was an excellent student, unlike some urban legends, but he was perceived as arrogant, and he dropped out of his German high school at age 14. One of his teachers kicked him out of the class, and when Einstein said, "I have said nothing against you," he said, "Your mere presence in the classroom undermines the students' respect for me." So he was apparently, I have so many fun stories, but I don't have time to tell you them. You could learn about them later. They're all in my book. Okay. All right. So so he actually taught himself calculus and did a lot, self-study, because he knew he could go to this Polytechnic University in Zurich if he just passed their exams. He didn't need his high school degree. Okay, and he does manage to get in. There's a few kind of twists before he gets in, but he excels for the first 2 years. He's the best student in his year. Okay, but then he finds that the professors are not being, they're not teaching him all the modern topics. They're kind of conservative. He stops going to class. He infuriates his professors. He refuses to call them Herr Professor. Apparently it's very insulting to say Herr Weber instead of Herr Professor. So anyway, he barely gets his degree, barely passes, and they intentionally don't pick him to stay. He wanted to stay and be an academic assistant. His boss, Weber, hired 2 engineers instead of Einstein. Okay. So he's barely got a way to feed himself for the next 2 years, but he has this friend, Marcel Grossman, whose father has pull, so he gets a job in the patent office in Bern, Switzerland, does a fine job there. He marries his fellow student, Mileva Marix. There's a whole interesting story there. She didn't pass her exams, Anyway, and he continues his physics studies while he's working in the patent office in the next 2 years. And by March 1905, he writes to his friend, I'm writing 4 papers at once. The 4th study is still a mere draft or concept. The electrodynamics of moving bodies by the use of a modification of the theory of space and time. And if you think it was normal then to talk about modification of the theory of space and time, it was not. Okay? That was a very strange thing to write to his friend, although it turned out to be true. Okay, so here we are. That's Einstein in a very brief nutshell with his Mileva. Okay, so this is the paper that's probably the most famous. And just if you're curious what his handwriting looked like, this is a handwritten version of it that he made later. And he wrote this paper in 1905 unaware of this paper by Lorentz that had many of the same things in it. Okay, so here he says in this paper that failure to detect the motion of the Earth relative to the light medium, that's the ether, leads to the conjecture that not only in mechanics but also in electrodynamics, the phenomena do not have any properties corresponding to the concept of absolute rest. So that's a complicated way of saying, again, if I'm walking at a constant velocity and someone passes me moving at a constant velocity, I don't know which of us is really at rest. Now this sounds like, you guys know you're really at rest in a certain frame of reference, but you're also spinning and so on. And there's a lot of technical details of exactly what that statement means, but it basically says that, if you were in a closed room moving at uniform velocity, not accelerating, where you would be able to tell because you'd lose your balance, that it was accelerating, and you did some experiment and everything was done, so you had no way to look outside, you wouldn't know if you had started moving before or anything. That's what the laws of physics would look the same. That was this idea of the principle of relativity, which actually it turned out Poincaré had already mentioned. He said, well, we shall raise this conjecture of the principle of relativity, I'm going to call this the principle of relativity, to the status of a postulate. I'm going to assume it's true. In addition, I'm going to postulate the only seemingly incompatible idea that in empty space, light always travels at the velocity c, which is v here in his old notation, but this is the speed of light, v in his notation. Okay, so he's saying that those two things are both true. Okay, but they seem incompatible. And later he wrote about this. Surprisingly, it only required a sufficiently sharpened concept of time to overcome the previous difficulties. So Einstein is going to change our concept of time. Okay. What? Okay. All right, so he did a little thought experiment, which in German, thought is Gedanken, the Gedanken experiment. Okay, imagine I have a weird clock. Okay, it's a clock where each tick is a light beam going back and forth once, right? So tick, etc. And that's my unit of time. Okay, and it's stationary. I'm looking at it. I'm stationary. It's not moving, and therefore the time between the ticks is the distance it travels divided by the speed of light c. C delta t is 2d, so delta t is 2d over c. Okay? Now, suppose I'm an observer and I'm moving at a steady velocity v, and this clock, and maybe an array of these clocks, is coming towards me. Okay? So now what I see looks like this, right? Because the clocks are moving toward me, so during a tick, this clock moves, okay, to these different locations. Okay. So in the frame where the clock is moving, the light path is not straight, right? It makes these kind of triangles. So the light path is longer than when it's just back and forth, but the speed can't be higher by the postulate that he gave us, that the speed of light can't change. So that means that the time between this tick and that tick should be longer. It should be longer. So that means that it's moving, the clock's ticking slower. Okay? So that seemed to be inconsistent. okay? This is just geometry. It's the length of a hypotenuse compared to one side of a triangle. So you can do like a 3-line argument, which I'm sure Zihan did very well in the test, and you can find out that the ticking time is the one for the stationary clock divided by this quantity, where this is the velocity of the observer divided by c. And if you want to do a little math here, when v is c, this is 0. 1 over 0 is infinity. So the clocks slow down and slow down and slow down until they're actually stopped if they could go the speed of light, which strongly suggests that they can't ever go the speed of light, which is one of the things we learn in relativity theory. Nothing can go the speed of light. Okay? So moving of clocks appear to run slow. It gets worse as v goes to c. Okay? And observers in the moving frame think our clocks are ticking slow. So that we actually, it's completely symmetric. If I had the same clock, he has a stationary clock in his frame that's I think is moving, he's going to see my clocks ticking slow. So, all right. And this equation and related equations called the Lorentz transformation were derived by Einstein, but they're called the Lorentz transformation because they turn out to be exactly what Lorentz. Okay. So Einstein said, as long as we accept that time does not flow equally for observers in a relative state of motion, then we'll be able to keep this principle that all the laws of physics are the same to all observers in different states of motion, and yet light still goes always at the same speed to all observers. That's the thing, was only seemingly inconsistent. But if we're willing to change how time flows and accept that different observers actually different times passes for them, which is very hard to visualize, then we can get away from this. And now, of course, we know this is correct. So what about these guys? They had the same equations. They both noticed that there was a weird thing that was kind of like time in their equations, but they couldn't accept that it was not absolute. So they insisted that this was an unobservable effect, and Lorentz said, well, it's some interaction with the unobservable ether that makes this happen. And I'm going to call this local time, but it's not real time. Okay. So the same math, but not the same understanding. Okay. Now Einstein goes further. He says in the second page of that paper, this is a 25-year-old guy, contradicting all the greatest physicists in the world. He says, the introduction of a light ether will prove superfluous inasmuch as, in accordance with the concept to be developed here, no space at absolute rest endowed with special properties exists. So he's saying, no, guys, you made that thing up, but there's no reason for it. It doesn't do anything for me here. All I have to do is believe that time has this weird property of not being universal and absolute, which Newton thought it was, and then physics makes sense. I don't need this unobservable thing that does nothing. Okay. Now we would say that's Occam's razor, and blah blah blah. You don't need things you can't observe in science. But anyway, but these guys who were much more famous and very distinguished and even historically famous couldn't make that leap. So that's an example of just clear conceptual thinking, radical, able to see. The emperor has no clothes. Guess what? There's no ether. Okay. But then, if you said that was true, if there's no ether, what are you disturbing when a light wave moves? Right? This is a wave without a medium. Then you took away the medium. So if you really thought about it, first you'd say, oh yeah, that was a stupid idea, the ether. But then you have to say, there's something that's a wave, but it's not a disturbance of medium. So that's weird. Okay? What could that mean? All right. Now, everything else in the theory that Einstein wrote in this 32-page paper was pretty much in Lorentz's work, except for one little thing. So he wrote another paper, not in this paper, and it asked, does the inertia of a body depend on its energy content? Anybody want to hazard a guess about what he might be doing in that paper? Anybody? Anybody? There's one thing everybody knows about Einstein. Right? Yes. E equals mc squared. So that he didn't realize it when he wrote the first paper, that there was this corollary that he could easily now prove, although Lorentz or nobody else had noticed it either. So here's his equation, and sure enough, this equation, which is not at all obvious, is equivalent to this equation. Okay. Well, this is, all right, I won't explain why it's equivalent, but this was also on the exam. But anyway, and he says the mass of a body is a measure of its energy content. Well, everybody's pretty up on Oppenheimer these days. How many people saw Oppenheimer? Yeah, so you know that this is really the equation that has to do with why when you split a heavy nucleus, you get a lot of energy out, or when you fuse a light nucleus, you get a lot of energy out. So this is really, the beginning of the nuclear atomic age. And there's a lot of story about Einstein. He even appears in that not so great movie, in my opinion. Okay, but what about this bizarre light wave without a medium? Okay, that seems pretty bizarre. So this is what he said in March in a different paper. He said, light is discontinuously distributed in space. According to the assumption to be contemplated here, when a light ray is spreading from a point, the energy is not distributed continuously over ever-increasing spaces. It consists of a finite number of energy quanta that are localized in points in space and move and can't be divided. They can only be absorbed or generated as a whole. All right, so this is actually what turns out to be the photon, which is the first force-carrying particle in the standard model of modern physics. People knew about electrons, which are in the standard model. They didn't know about any other fundamental particle besides electrons, but they knew this was the photon, and of course, quanta, it's related to quantum theory, and so on. And the whole story of this is a big part of what's in the book, if you're interested. But you should know that all the particles of the standard model, it's our basic theory of the universe, are fundamental waves like this that are not disturbances in a medium, unless you invent some new ether, okay? And so things that are wave-like without a medium are exactly what we call fundamental particles in modern physics, and that's why there's all this talk about wave-particle duality in quantum mechanics, although I would just say the waves should be saved for the classical waves, and the particles should be saved for pieces of dirt or cannonballs, and this is just a quantum object. You shouldn't confuse people by calling a particle or a wave. That's a long conversation, which I will not go further into. But anyway, so Einstein did all of this conceptual change, talking about light as being really a particle and eventually being correct in a very complicated, subtle way that took 20 years to sort out. All of this was not math. It was insight, it was physics, it was concept, it was logic, intuition, all wrapped together. And there was math, of course, somehow. Okay, so that's a little bit about Einstein's miracle year and conceptual thinking. So the greatest physicists and mathematicians of the time had done the same math, but they got different physics out, and Einstein got what we now believe is the correct physics out. Okay, so now we go back to the mere mortals. Okay, so 100 years later, 2005, I'm puzzling about a new kind of laser, which was invented by my colleague here, Wei Cao, who pioneered what's called a random laser. Okay, and we need to review what a laser is, which is a very interesting thing, if you don't know, before we can understand what the puzzle is. Okay, so maybe I should stop though. Do you have any questions about Einstein? I mean, there are a million questions you could ask. And we will have questions later. But if there's anybody has a burning question about the first part of what I did, yeah.
What do you think Einstein's preliminary research did as far as optogenetics is today? By the way, my name's Anthony Ross.
Well, I don't think I have much insight about that. I barely know what optogenetics is. But the whole kind of, we will see in the rest of this talk that the whole way we think about the absorption of light is come from Einstein with some help from Bohr and people. And so that the framework, all the way you would see people talking about, light interacting with matter, started with the work I'm going to tell you about by Einstein, mainly, a little bit by Bohr too. Okay, so that's about all I can say. In other words, quantum mechanics underlies everything we're doing. Okay, and that's what we'll talk about. Okay, so what's special about laser light? Okay, so where do we get light from on Earth? Well, we get it either from the sun or we burn things, and that's what we've done for the first 100,000 years of humanity. And then, last 130 years, we figured out how to run a current through a wire and make a very hot, dangerous source of light. Okay, and I won't include, there's now, of course, LEDs, which are really like very closely related to lasers, so I won't talk about them. Okay, so, but the last 65 years, we've had this uniquely pure and beautiful source of light called a laser. And it's the most orderly kind of light you can have, and it has a very specific wavelength or color or frequency. Okay, and here is somebody interested in lasers with somebody who more or less is the father of the laser. This is Charles Towns, and this is York Street, right, pretty near us. And he came and spoke at Yale, and I got to meet him and talk to him about lasers. I also got to ask him if he had met Einstein, and he said, oh yes, many times. So that's pretty cool, right? By the time I started working on Einstein, all the people that really knew Einstein were dead. The people would come up to me in Princeton and they would say, oh, I saw him taking, walking to the office, when I was 10. But nobody had ever talked to him about physics, right? Because they were all dead, all right? But not this guy. He was, it's not like that. But anyway, nonetheless, I didn't learn anything really new, but he had seen him at conferences and talked to him privately and everything, so it was kind of cool. Anyway, he's the father of laser. He's a great, brilliant man, and I won't get to tell you much about him now, but it was cool to meet him. Okay, so light, according to Maxwell, is an orderly electromagnetic wave. How do we make orderly electromagnetic waves? Well, like 20 years after Maxwell, Heinrich Hertz in Germany, and then 10 years later, Guglielmo Marconi, made commercial radio. Heinrich Hertz did the first radio, and then by 1899 there was really radio. This is an example that we even crossed the Atlantic and so on. And what you do is you have some kind of energy source. You create an oscillating current, and it drives a dipole antenna, and there's some current there that jiggles up and down if it's going to jiggle, and that jiggling is the source of a radio wave, and the radio wave goes out with the frequency of the jiggling of that current. Okay, so we know how to do that, okay, but now this generation, you all know what megahertz and gigahertz are, right? Everybody knows because they're buying things. And do you know what is the typical range of frequencies you would use on your cell phone? What? How many gigahertz or a few gigahertz? What? Anybody know? Okay, anyway, the point is cell phone is gigahertz, right? Radio is megahertz because that was earlier technology. We could not make gigahertz things that were in your hand until 1990. I mean, it's pretty recent that we could even do that. Now, of course, all the cell phones are gigahertz. But that's still 10 to the 9th cycles per second. Okay, so let's get there. Okay, so a radio wave and a laser-generated light wave are basically the same thing. The only thing, it's very ordered, one frequency, very controlled field that comes out, but light is 1,000,000 times higher frequency. So forget about your gigahertz, you need 100 terahertz. 400 terahertz, sorry, for visible. So that's a million more, 4 million times higher frequency, and we can't do any electronics that does anything like that. So the only thing that jiggles that fast are atoms. And they jiggle that fast when they emit radiation. So how do you generate an AC current in an atom to make it like a little antenna? Well, you could do it, but you have to get them all to work together. One atom is not going to give you laser, right? They have to all work together, sync them. So of course, nobody knew how to do this for a long time. First, we had to invent quantum mechanics. Here's a bunch of the famous people that did it, including Einstein and Heisenberg and Schrödinger, blah, 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 Niels Bohr. And we did end up understanding the atom. So the atom, there's a nucleus here, and there's a cloud of electrons in an orbit around it. Okay, here they show them as little particles, but we now know they're kind of a cloud, right? And I won't go into that, but there's something called a wave function psi, which describes this cloud of where the electron might be, sometimes called a cloud of probability. And even though the electron is cloudy, its energy is actually quantized, hence quantum theory, with different levels of energy. Okay, and you emit light when the electron in one of the higher energy levels drops down spontaneously and just sends out light, and the light has a frequency related to the energy difference of the level divided by this thing called Planck's constant, which is the kind of thing that tells you your quantum. And this amount of energy is much more, you know, it gives you 400 terahertz. Okay. Okay, so this is equivalent to an oscillating current in an atom, but now you have to get them all to work together. Okay, so we're back to Einstein. See, I do have something to say. I'm working with him. We're together. So in 1917, he looked at what Bohr had done, this idea of energy levels. He said, well, imagine I have a bunch of atoms. I'm only going to look at 2 levels for each atom. So each pair here is a different atom. And I send in a photon, I'll say, and there it gets absorbed. That's absorption. Okay. And also I can just fall back down, and it's going to emit. I don't know why it's so slow. And that's called spontaneous emission, where nothing causes it. But if I have an electron in the excited level, and a lot of photons come by, and they all have the same frequency, etc., it's going to de-excite that electron and create another one. That's called stimulated emission, and that creates a copy of the light that came in. So if you have a situation, there's Mr. Towns, where you have lots more of the atoms have energy than don't, then when you send in light, okay, you have to pump the atoms to get that. I won't go into that. So now light comes through, and it creates both some absorption and some emission, but there's more emission because there's more atoms in the upper level than in the lower level. So there's some absorption, some emission, but there's more emission. So it amplifies the light. So this is the origin of the acronym, oh there, light amplified by stimulated emission of radiation, laser. Okay, so that's good, except that's not really what we mostly call a laser these days. Okay, because a laser is a light source, it's not an amplifier. Okay, now there are lasers, I won't go into how this terminology changed over the years. Okay, so it's a source. So what you do there is you still pump it and put all the atoms in the excited state, but you just put some mirrors around it, and these things spontaneously emit, and then they bounce back and forth. Again, I don't know, the simulation should not be nearly as slow. Some of it comes out as light, but some of it goes back and creates more and more, and you get this kind of chain reaction where this thing organizes, and we call this a self-organized oscillator. So it's a light oscillator by stimulated emission of radiation. And for some reason, this didn't catch on as the name of this device, so they just stuck with laser. I can't understand it. Anyway, okay, so that's all the background on lasers. So in the 1990s, my colleague Wei Cao was taking a little chunk of a little nanoparticle particles called zinc oxide. And she was pumping it, so it was inverted. It emits a lot of light, but there are no mirrors. So there's no kind of like bouncing back and forth and interfering the way there was in my little simulation there. So people didn't really expect this to act like a laser, but it did. There, this narrow peak in the intensity at a certain wavelength or frequency tells you that it's a single color and it's characteristic of laser. I can tell you many more details if you would love, knew the technical definition. You can prove this is a real laser. Very weird laser. It emits in all directions. Doesn't emit a nice beam. Okay. The question was, is this really a different kind of laser, or can it be understood by the same picture as before? Okay. And some people, I will not name them, were saying, no, this is a new kind of laser that doesn't need interference to work. And I was very skeptical of that. So I said, okay, I'm going to try to figure out how to have a theory of this kind of laser. Okay? Can we mathematically model it and predict its properties? Okay. And 10 years later, sparing many, many details, I was relatively successful, and I can say confidently that it's not a new kind of laser. You still need interference. It's just the interference is too complicated for you to easily describe. This is the result of a calculation we did, this nice artistic rendering of a random laser that we actually calculated. This is how it would emit, and I'm not going to attempt to do more detailed stuff, but it's a cool picture, and because we did the underlying math, we kind of understand much more about how it works. But because we had to think about what defines a laser, some new things occurred to me, us and me, about the symmetry properties of a laser. And it turns out each laser has a twin, which you could call an anti-laser, okay? And so I did my own kind of Gedanken experiment. So here's a typical laser. I have a gain medium, I put in energy, light gets generated, it bounces around, and out comes this nice coherent pattern. And I was trying to explain this mysterious self-organization of a laser where it just kind of finds what it needs to do. Why is this? That's weird. Okay. I don't know why the laser disappeared, but it's really doing these, sorry, these little animations badly, sorry. Okay. So I was trying to explain to somebody, I found this very puzzling, so I was explaining to my colleague, well, if you don't like thinking of it this way, of it just sort of mysteriously self-organizes, why don't you think of a different thing? Imagine you put exactly the same light beam in, and instead of having atoms that are all in the excited state, you keep them in the ground state, so they're going to absorb. But you have exactly the same amount of absorption as you had amplification here. So that's gain, balancing, loss. Then you send in exactly the same pattern, and it'll get perfectly trapped and absorbed. And that's like running the laser backwards, okay? And that was really to explain it to somebody and to myself, okay? And then I said, hey, I wonder if people know this. I mean, I never saw this in a book, right, about lasers. I never saw this. So I was like, I wonder if people know this. And I'm walking down the corridor, and I'm saying, hey, wait, have you ever heard of this? And, do you think it's, and so nobody knows if anybody knew this. So eventually, the important thing is that, well, first thing is that, after not finding anybody that knew it at Yale, I called the kind of real laser mavens at MIT, and I said, I'm coming down, I want to tell you this idea, tell me if this is like a known thing, okay? So it's very exciting. And I sat with these people. I won't tell you who they are, but they're very distinguished. And I mean, I would tell you, but you wouldn't know it. And finally, one of them, Marin Siljacic is his name, said, well, it's kind of like this, but it's a generalization of X. I won't tell you what X is, but there's a lot more details. So there was a very simple version of this that people had noticed, but they didn't realize it was the time reversal laser. So they knew you could do this, but they didn't realize that. And what they didn't realize is if it works for this simple laser, it's going to work for a really complicated laser too. This is called a completely general exact statement about electromagnetism. Those don't come along that often. Okay, so let's just generalize this to two mirrors. Okay, so you have two mirrors that can emit, and now the light comes out symmetrically instead of out of only one side. Okay, two equal mirrors, output mirrors, they call them. And now let's put loss there. Well, in order to get it to absorb, I have to send in two beams. And they have to be just right. They have to be balanced and coherent to get trapped and lost and absorbed. So that's the thing that nobody had actually done, even though it's such a simple experiment that once you think about it. So the energy comes out and nothing bounces off. Everything has to be tuned correctly to get this to work, and no one had ever done this experiment. So the tuning, well, the beams needed to interfere correctly, right? So we talked about interference when we had the water earlier. So here, it's got to be a kind of constructive interference to work, and if you don't have that, it won't work, okay? So if you don't have it, if you do have it, it works. You don't have it, a lot of the light just goes through. Wait, I don't know why again, my simulations aren't working. Okay, anyway, if it's not in phase, it won't absorb. So it only absorbs a very specific pattern of input. Okay, so we call this coherent perfect absorption because you have to put in exactly the right interference pattern and then it'll absorb. Otherwise, it might not absorb at all. It might absorb negligibly. So this was a new thing. So we then did this experiment, which came out in Science. And here's our laser. Here's our silicon wafer, which is going to, for various reasons, function as our coherent perfect absorber with the two kind of output mirrors. And this is something that allows us to change. We split the light from the laser. So it goes in coherent, but I can make it out of phase by changing this little leg here so it interferes differently. Okay? Okay, so then that wafer is the thing which I'm going to have to send in and hope nothing comes out. Nothing reflects, it all gets absorbed. Okay? So this is when I have the wrong phase, which is here, between the inputs. So then it isn't absorbed, it's scattered, it just reflects. Some transmits, but it doesn't get absorbed. And then as I change this control here, I see that it goes down and it's almost all absorbed. So that was the experiment that showed this very simple generalization of coherent perfect absorption. Okay, and it got into Science, and you know, when you get something in Science, then the Yale press office wants to write an article about it, and so I came up with this term. They didn't like coherent perfect absorption because it sounded technical. They wanted me to call it something else, so I said, call it the anti-laser. Well, the internet loved the anti-laser. So there, you know, within a very short period of time, there was, whatever it was, millions of hits, and it was written up in, New York Times and Popular Science and the Wikipedia entry. But the real high point for me, very meaningful, was the Fox News. And I talked to the lady, and then this is what she came up with. Dear James Bond, next time a laser beam threatens to cut you into, try switching it into reverse. So it was a very great explanation of what I had done, and I don't know, anyway, so that's what she came up with. Okay, so last slide. What could this be good for? Okay, it could be good for the following kind of situation, where you might want to do something biomedical. Okay, so here's a situation where I have an absorbing piece of material that's shielded by a lot of pieces of material that just scatter light and are like a shield. Okay, this is a real calculation we did, and normally, if I asked you, could I actually get all the energy in from outside and get all of it to get absorbed there, you would say that's impossible. Particularly if you knew something about light scattering, you would have to not somehow feel all these outer things that should reflect it, right? Well, we know it's possible because we know if we put enough gain there, it would emit laser radiation as a random laser. So we just know how to calculate that this is the pattern that is not moving very well because of the weird slowness. But anyway, this is the animation of the, that's probably this screen that's something, because this works fine on my laptop. But anyway, it's coming in and it's being absorbed, and you can tell that it's a really weird pattern that you would never guess that works. And that's the main point. This is basically something that we didn't know you could do till after the work on coherent perfect absorption. And as I mentioned here, you can do, besides this kind of thing, you can control the flow of light on a chip for AI or sensing or so on. So there's really some hope that after it's now quite a while later, and this has progressed and so on, and people are looking at applications. I want to thank my collaborators, Wei Sao, former students, postdocs, that's collaborators, and of course, Albert.
All right, let's thank Professor Stone again for coming out. I know that we've been sitting for a while, so why don't we stand up, stretch, find another seat, and then, actually, sorry, we should take questions. You're right.
Okay, so
We'll take a...
floor is open for questions.
We'll start right here.
My name is Ryan Smith. I'm a physics major at North Carolina A&T. I wanted to ask, how is this different from the Michelson interferometer experiment?
So Michelson interferometer experiment is, there's no absorption involved, right? So this is like an absorbing interferometer. It is an interferometer, like you said, but it's an absorbing one. And the simple setup, you know, in Michelson, what they do, this was an effort to actually measure the change in the speed of light based on the direction of the Earth's motion that was historically important. And so they send light and they split it. Some of it goes sideways and some of it comes back and forth. And if light was moving slower this way than that, then you would see a different pattern of interference. So they both involve, obviously, interferometry. The thing is that interferometers are usually very simple. And the picture I showed on the last page of a complicated aggregate where the light is scattering many times, you can't guess what's going to happen there, right? So interferometers are set up so you can just trace rays and figure out what's going to happen. That's impossible. People thought there was no analytic approach to that kind of problem. And what our work did was it showed that there is an analytic approach. You have to use essentially laser theory to figure out what the special input is that will do the interference you're interested in.
I'm Jesse Olson. I'm from Florida State University, and I work at the National High Magnetic Field Laboratory. I've done some work in quantum optics and NMR, and I wanted to ask you more about the specific theoretical details that you omitted. I'm aware that something like the Lagrangian master equation with different choices for the jump operators might be able to model something like this theoretically. Could you talk a little more about how your group did that?
No. Sorry. So this is not quantum optics. This is classical optics.
This is a purely classical problem?
This is a purely classical.
So you use classical stochastic simulations then?
You use laser theory. I mean, I can tell you what we did.
Ah,
Okay. So so that's why quantum optics is very subtle. So we have no, we don't need photons here.
So this is a totally non-quantum phenomenon? You could just use a classical description of light?
Yes.
Wow.
You can use Maxwell's equations. You need quantum matter, but you don't need quantum light because we're not studying fluctuations. The whole point, and sometimes it's not taught very well, is that all the quantum words that people use only apply to the fluctuations in the light fields. If you want to know the average behavior, then you can just use Maxwell's equation. But the other thing is that when you have zero, it's zero for all fluctuations. This is zero. So this effect happens in quantum mechanics. Okay, if I had an infinitely sharp line, infinitely sharp input line, then I would have a 0 even in quantum optics. But because my line is finite, there'll be some, you have to have the right frequency. Anyway, there's more technical. I won't go more technical, but this is classical. Sure.
My name is Raza. I'm from Livermore, California. You've heard of us.
Yeah, I've been there.
So,
To the lab.
yeah. I wanted to ask about the biomedical applications. You mentioned that briefly. Where do you think you could use an anti-laser in those kinds of applications?
Well, first, I mean, you have to have a tremendous amount of knowledge to actually send in the right thing. So it's not immediately practical. We had total knowledge of what was there, so we could adapt the waveform to go through. Okay, but there's a tremendous amount of work on kind of diagnosing what's there from sending in light and varying the light field, and then eventually stimulating certain neurons, or just doing things deeper in the brain than you can now do. And this is being done here at Yale. It's not the same as coherent perfect absorption, but it's closely related. Finding special interference patterns that get you to a place that you normally couldn't get to. So that concept it's being widely explored. We have papers on it that, yeah.
All right. Just joining one more time and thanking Dr. Stone for coming. All right, and I'm sure he'll stay back after the next talk if you want to talk more in depth.
Oh yeah, are we starting right away with the break?
Yes. So what we'll do is everybody can stand up, stretch, find a different seat,
You can ask.
and then we'll set up Dr. Lakshman Narayan.
Okay.
It's like mostly.
I think that was friendly.
Did you make it out last night?
No, I actually.
Oh, oh wait, so like what I said earlier, like yes, he was like the nicest guy ever. I was just like, I'm representing him. You were like, I don't think of others.
Yeah, he is. Do you know him?
Well, I'm from Tallahassee. I did a middle school operation.
Are you serious?
Yeah, I worked there when I was in middle school.
That's amazing.
A lot
I
of
was
them
in
are
Shy
social groups
Girls
are like
too.
related.
That's amazing. Where did you go to school?
I went to Florida High.
Oh, that's awesome.
Yeah.
Yeah, I know some people.